in chapter 7, we will introduce potential energy in addition to kinetic energy. And here I say conservation of mechanical energy. Mechanical energy is nothing but kinetic energy plus potential energy. And this mechanical energy is not always conserved. It's conserved only for certain forces. That's conservative force. For non-conservative force, this mechanical energy is not. We will also learn potential energy curves as a function of position, which is very important part of this. Also important part of this. Then what is the definition of conservative force and non-conservative force? The work done in moving between 2 points of an object by a force, if it's independent of the path, that's conservative force. Okay. For example, when you move an object from point A to point B, following this path or this path, any path, it doesn't matter. So the work done by the force only depends on the initial position and the final position, regardless of which path it follows. Then that force is conservative force. Then, for example, if you make a closed loop like this, the object starts from here and following this path and comes back to the original position, because the work done by force, conservative force, only depends on the initial and final position. It means this object doesn't move. Same as this object doesn't move. So force due to the conservative force, work done by the conservative force for closed path should be 0. Okay? For non-conservative force is defined as the force for which the work done should depends on the path. For example, which path it follows, not only the initial position and final position, the work done by the force depends on the path, which path it follows. Okay? So in that case, work done going around the closed path doesn't have to be 0 in this. For example, gravitational force, electrical force, Coulomb force, okay? Spring force, and such. This kind of force, actually, if you look at later we will learn the gravitational force is r square m1 m2. And then electrical force is also r square q1. Spring force is minus kx. What are the common things? So non-conservative force example is friction. Friction is, so conservative force here is actually function of position. Force is function of position. In that case, usually it's conservative. Okay? The forces are function of position. Then the work done by that forces does not depend on the path, which path it follows. So this place only depends on the initial and final position. However, for non-conservative force, this frictional force, for example, does not depend on the position, but it depends on what? The velocity vector. Right? So which path it follows, the force direction changes, and also the total displacement changes too. So we define this quantity and put minus sign, define this as a potential energy. Okay? And here A we call a reference point. Why? Because when x equals A, potential energy is 0. So A is a reference point where we set potential energy is 0. Okay? So what is potential energy? We define potential energy like this. And what does that mean? What does this potential energy mean? It means stored work associated with a conservative force, only conservative force. Non-conservative force, for non-conservative force, we cannot define potential energy. Later, it can be released as kinetic energy. I will show that later when I explain the mechanical energy. Definition of potential energy is given by this equation. Negative of the work done by a conservative force. Negative of work done by conservative force from the reference point to a certain point. So if we want to find out the potential energy at x, that means minus work from the reference point to that position x, that force, conservative force did. Okay? And so potential energy value can change with choice of reference point. So what really physically means meaningful is just change in potential energy, because we can change the reference point at our convenience. So delta U is what is really meaningful. Absolute value is not really meaningful. We are free to set the 0 of potential energy at any convenient point, reference point. Conservation of mechanical energy only holds for conservative force. Net work done on an object is equal to kinetic energy increase or decrease, kinetic energy change. This always holds, okay, for any kinds of force. But this definition of this potential energy is only holds for conservative force. Delta U is minus net work done by the net force. So only for conservative force, we can combine these two. When the force is only conservative, you can combine these two and conclude that delta K plus delta U is 0, while the force is acting. Equivalently, we can say that K plus U, which is kinetic energy plus potential energy, before and after the conservative force acting, conserved. Okay? So now we can define this K plus U, kinetic energy plus potential energy, as mechanical energy. This mechanical energy is conserved for conservative force. Okay? The spring force. The spring force is conservative or non-conservative? It's conservative. Then we can say mechanical energy is conserved or not. Mechanical energy conserved, right? Before and after the force is exerted, so initial state and final state, mechanical energy, which is kinetic energy plus potential energy, should be conserved, should be equal. At initial state, what is the mechanical energy? Because this dart doesn't move, there is no movement, initial velocity is 0, all the mechanical energy is potential energy stored in the spring, which is 1/2 kx. X is compressed length compared to the equilibrium length of the spring. And what about the mechanical energy at the final state? Spring is released, right, to the equilibrium length, so potential energy of the spring is now 0. Final state, at the final state, dart is moving. So K plus U is 0 at the final state, which is 1/2 mv squared. And these two should be equal, right? So what we can say is that initially potential energy is stored in the spring. Now that potential energy is released into kinetic energy. I told you that potential energy can be released into kinetic energy. Due to this conservation of energy, mechanical energy, you can easily see that mechanical energy, the potential energy stored in the spring is released into kinetic energy of the dart, right, of the system. You can find from this equation easily the speed of the final velocity of the dart. Without using this mechanical energy conservation, this problem may not be very simple to you can still calculate the velocity, but it's much easier if you use this mechanical energy conservation. So conservation of mechanical energy is a very good tool to think about and solve some problem in everyday life, like many problems only involving the conservative force. After leaving the spring, in this curve, potential energy versus position curve, it basically express what is the potential energy at each position. And the total energy, let's say total energy is fixed, total mechanical energy is fixed. Then what will be the motion of the object? For example, here, where is the speed? Kinetic energy. Basically, kinetic energy is 1/2 mv squared, proportional to v squared. So speed is proportional to v squared. Where is the speed maximum among A, B, C, D point here? When total energy is fixed here, and total mechanical energy is conserved. Then we know U plus K is constant. So when potential energy is greater, then kinetic energy is smaller. So kinetic energy becomes maximum when potential energy becomes minimum. So among A, B, C, D, where is the potential energy minimum? You can see easily that it's D. Now, if the total energy is less than, at some point, less than the potential energy, then what happened to the motion of the object? Because the potential energy is greater than the kinetic energy, and K plus U is the total energy, and this object cannot be located at this position where potential energy is greater than the total energy, because K cannot be negative, right? Kinetic energy cannot be negative. So what that means is that the object will move only between these two regions. We can say this 2 point is the returning point. An object is trapped in between these two positions. We can say it's a potential well between the position where its total energy equals its potential energy. For example, here, even the total energy is lowered, then the object will move between these two positions here, because at this here, potential energy is greater than the total energy. Now this object will be confined between these two positions. These are turning points. Later, when you learn quantum mechanics, it's a little bit different, but Now let's focus on the classical mechanics. So potential energy in one dimension is defined as net work done by the force, and put negative sign there. So if we know potential energy versus position graph, we can find force, because opposite to integration is there. And also here, from here, in 3D, you're not going to really calculate this three-dimensional force, but you only need to know the constant. So from the potential energy, so you can find actually from here, in this graph, A, B, C, D, where is the force maximum? And force, which direction is the force? Positive direction or negative direction? It depends on the slope. So negative of the slope is the force at that position. So think about the direction of the force and the magnitude of the force at each position. Okay. Here's the end of this lecture.